So we've been studying motion for a while now. We've looked at the kinematic equations. We've done a lab involving constant velocity motion, which I hope you guys are still analyzing. And we've looked at the definitions of velocity and acceleration and displacement. And kind of the last part of this one-dimensional motion chapter is how we can look at graphs of motion and interpret them. In other words, look at these graphs and kind of explain what's going on in them. So one of the first types of graphs we looked at were these position versus time graphs. So you can imagine that we have this graph of position versus time. So let's see, maybe right here and then over. Just a very simple graph. So we'll have time on this axis. We'll have position x on this axis. And say at time 0 seconds, we see a slant up to maybe 3 meters at 3 seconds. And then it flattens out to 6 seconds. Then we see it sloping kind of down like this. So it goes to 1 meter. This is obviously not to scale. So it goes to 1 meter at, let's see, what should we make this? Let's make this 10 seconds. Okay. And so we'll just go from 0 to 10 seconds, and we have kind of these points in the position time graph. And what we want to do is we want to interpret that. We want to tell or say whether the object is going backwards or forwards, and what the velocity is. So as mentioned before, you can look at the slope of these position time graphs and you can get velocity. So maybe at this part right here, the first question is, well, is it moving forward or is it moving backwards? And the way we can tell on a position time graph if it's moving forward or backwards is the slope of the graph. If the slope is positive on the graph, then the object will be moving in the forward direction. And if it's negative, then it's moving in the backward direction, because a positive slope indicates a positive velocity. So it's moving in the positive direction, which, I should correct myself, is usually forward. And then if it's got a negative slope, like over here, then it's moving the negative direction, which is usually backwards. And in this part right here, where it's totally flat, it's come to a stop. Okay, so there's no change in position over this time, and so the object just come to a stop. And so we can say, okay, here it's moving in the positive direction. Over here, it's moving in the negative direction. Then here, it has just come to a stop. And if we want to calculate the velocities, well, then we look at the slopes. So we take maybe this point right here and this point over here, and we do rise over run for slope. So essentially this velocity, the magnitude, so these two lines next to a quantity, I'm just talking about the magnitude. I'm not talking about the direction of it. So the magnitude of the velocity would be this 3 meters. Okay, so this would be my final position minus my initial position, which is how we do delta x. Okay, divided by the total time. So it's going to be 3 seconds. So for that section, that velocity is going to be positive 1 meters per second. Okay, and as we said over here, it's stopped. And then over here, it's velocity. We have a change position of 3 to 1. So our final position is 1 meter. Our initial position is 3 meters. And this time change will be 10 seconds minus 6 seconds. So we have negative 2 meters over 4 seconds. Okay, so this will be negative 1/2 meters per second. Or, since this is science, we don't use fractions in science, so they will say that this is negative 0.5 meters per second. Okay, so that's how you would interpret a position versus time graph. You can get velocities from it, and you can tell whether it's moving forward or backward by the slope of those lines. Now, let's take kind of the same graph here, the same graph, and let's look at, instead, let's change our axes. Let's, instead of having position versus time, let's make this a velocity versus time graph. Okay, so I'm going to still start at 0 seconds and maybe have 3 seconds, 6 seconds, and then 10 seconds. Okay, and we're going to go up. Now, instead of going up to 3 meters, we're going to go up to 3 meters per second. Okay, so it's going to go up like this, and then it's going to flatten out, and then it's going to go down to 1 meter per second at 10 seconds. Okay, so how has this changed? How does the fact that I've changed my vertical axis to velocity change how I'm interpreting this graph? And it's really actually kind of significant. So in this case, the slope that I'm measuring, I'm going to write this over here, the slope in a velocity versus time graph gives acceleration. Okay, so it gives you the acceleration. Okay, so all these slopes that we're looking at now, instead of giving us velocity, like it did in the position time graph, it's going to give us accelerations. And later on in calculus, you guys are going to learn about derivatives if you haven't learned it already. And so what we would say is that if you take the derivative of a function of velocity as a function of time, then you would get the function of acceleration. And if you take the derivative of a function of position with time, you would get velocity. Okay, so these are just kind of derivatives of each other. So anyway, so this one, we would say our acceleration, in this case, our acceleration would be essentially a positive 3 meter per second change over 3 seconds. So our acceleration is positive 1 meter per second squared. So remember that's the sign of the acceleration. Here, my acceleration has a slope of 0, so that's going to be 0 meters per second squared. And then over here, I'm not going to write this out, but before we found out this has a slope of negative 0.5, so that'd be negative 0.5 meters per second squared. Okay, pretty straightforward. Where this really has a difference in interpretation, though, is whether the object is moving forwards or backwards. Okay, so I want you guys to know something. In this entire section, this whole section, the velocity is always positive. Okay, so this whole section, whether it's a positive slope, a slope of 0, or a negative slope, it is moving with a positive velocity, which is usually the forward direction. Okay, so you don't tell by the slope whether it's moving forward or backwards. What you would tell by, I'm going to extend this out a little bit, is once this goes down, right here, it would have a velocity of 0 meters per second, so where it crosses the axes, you would say it has stopped. And then here, it has a negative velocity, and so if the negative direction is where it's going backwards, then it's going backwards when it's underneath this x-axis. Okay, so you don't tell by the slope, you tell whether it's above or below this x-axis. Furthermore, this part right here, okay, it's flat, but it doesn't mean that it has stopped. Notice it's still moving at 3 meters per second in this section right here. So what that's saying is that it's moving at a constant 3 meters per second. In other words, the velocity is not changing, but it's still moving. Because the velocity is not changing, it has 0 acceleration. Okay, but it is still moving. So usually students have problems with this velocity time graph. They can get the slopes okay, they can calculate the accelerations okay, but when I ask them to say whether it's moving forwards or backwards or whether it's stopped, they really have trouble with it. They keep on wanting to say that this right here means it's moving backwards. They want to interpret the velocity time graph just like they would a position time graph. So be very, very careful about that. Make sure you know what your axis is, whether it's velocity or position, and then remember the difference between how we interpret forwards, backwards, and stopped with these two graphs. And if you have any questions, please let me know in class.